Good morning. Yeah, welcome back everybody, and a little something different today. Another tech talk because I am not going to be here on Saturday. I'm going to be out of town with my family, and I should have put out a community post, and you'll know why. But yes, so I figured I'd give you guys another tech talk video. So today's is going to deal with electrical power, or as one of the commenters sometime back said, the ability to speak electron. That gave me a chuckle when I read that one. So we're gonna learn on the electrical system here in the F4, and a lot of this does apply to other airplanes, not just the F4. So let's dig into this. All right, now the electrical system in the F4 and a lot of aircraft are comprised of multiple systems. And as you can see here on the breaker panels, and we got multiple breaker panels. There's panel 1, 2, 3, 4 is over there. There's multiples of these. But it's a combination of both AC and DC electrical power. And this is a lot more complicated than what you would find in your home. So let's take a slightly deeper dive into the differences between the two and how they all operate. All right, now DC power is fairly easy to understand. DC stands for direct current and is the power that you would find coming off of a battery. Most people understand batteries. You get two terminals, a positive and a negative, and you get some sort of voltage out of it. 12 volts in this one's case. This one's battery gives it 24. The little AA batteries that go inside your remote control are typically 1.5 volts. But you get the idea of it. It's just a straight pure voltage coming off of that battery. All right, the other form of electrical power is AC power, which stands for alternating current. This is the power that comes off of a generator. The reason it's called alternating is because the voltage will alternate between a positive and a negative voltage as during its rotational cycle from the generator itself. And the speed of that generator determines its frequency, also known as hertz. So like here in North America, it is 60 hertz. Some countries over in Europe is 50 hertz or 50 cycles per second. And a cycle is when the waveform goes from 0 to its positive peak, back to 0, its negative peak, and back to 0. That's one full rotation of that generator. Now, aircraft use 400 hertz power. So there's a reason for that, and the short and sweet of it is 400 hertz power allows generators to be built a little smaller, so they weigh less, which is a very important thing in aircraft. And you can get a fair amount of energy out of that smaller package too. So that is a specialist form of electrical power. So you can't just take a power source and just plug it straight into the aircraft. That requires some specialized equipment like our generator cart here, or the Dash 60 with its generator. Or if you got a really nice hangar, have a power source from the utility power going into a phase converter and power the aircraft directly that way without needing diesel fuel or jet fuel in the case of the Dash 60. All right, so let's take a deeper dive into generators, as I think it may have confused some people, and I can definitely help simplify this. All right, now we'll start simple with a small generator, much like the one I keep here at home. This came in incredibly handy during Hurricane Beryl a couple months ago when our power got knocked out thanks to the storm. And we were able to keep our refrigerators cold, and I even later that evening took out the margarita machine and cranked us out some pina coladas that night. So ran pretty well, and this little guy is, like I said, it's almost as simple as generators can get. You have an engine driving an alternator, and it creates electricity. Well, the way it creates electricity is actually quite simple. So here on the screen, I got a little diagram that I drew up, If you take a magnet, and it will always have a magnetic field around it, if you take that magnet and spin that past a coil of wire, what's going to happen is, as that magnetic field, and remember it's got a north and a south pole, whenever that magnetic field passes through that coil, it's going to create electricity. And with the way that this does it, it creates alternating current. Now let's look at this. So as the magnet spins past, and remember this is rotating because the engine is driving it. If we plot this over time on a little graph here, let's call this your positive voltage, a negative voltage. This middle line here is 0, and the x-axis here is time. So as the magnetic field starts to come around and move past the coil, what's going to happen here, if you measured this with a meter, and you can, or even better, an oscilloscope, which you can actually visually see this, what's going to happen is the voltage in the coil is going to start to rise, and then as the magnet comes 90 degrees to it, it's going to peak and then start to fall as that magnetic pole ends up moving past the coil. Now the south pole's turn to come around is going to happen as well, and that's going to draw voltage and current going the other direction. So it's going to pull this down into negative as it spins around, and it's going to peak and then return back to 0. And that is one revolution of that magnet past this coil of wire. And what you end up with is what's called a sine wave. This is one full cycle because that's one full revolution of the magnet. So when you get a positive peak, a negative peak, and back to 0, that's one cycle. Over time, like in the case of my generator, the engine turns at 3,600 RPM. That's 60 times per second, and since the alternator is bolted direct to the alternator, the rotor inside that generator spins also at 60 hertz. That is what creates 60 hertz. So you get 60 of these each second, hence 60 hertz power. If the engine on my generator was spinning at 3,000 RPM, it would make 50 hertz power, very common over in Europe. My generator creates 240 volt electricity across its coil. So if I measure from one lead to the other, I would get 240 volts AC power. Well, hang on a second, you might say. A lot of my stuff in my home runs on 120 volts. Yes, it does. And let's come up with another diagram for this. Alright, so we have the same stator coil, and that's what it's called on the generator. The rotor is what's being spun by the engine. The stator is the coil that's stationary outside of it, that surrounds the rotor. So in my case, like I mentioned, you get 240 volts from one side of the coil to the other as my generator runs. Now, how do we get 120 volts out of it? Well, if we center tap the coil like so and split it, you're effectively splitting it in half electrically. And one half of the coil will create 120 volt from here to here. The other half will also create 120 volt from there to there. Now, some large devices, like say some stovetops, a clothes dryer, air conditioners, they run on 240 volts, so they wouldn't connect to the neutral, and that's what this wire would be called, is the neutral, because it's literally in the neutral position in between both halves of the coil. So something that requires a much higher voltage will only connect to the actual sides of the coil. And here in North America, this would be called L1, and this would be called L2, like in a circuit panel. So this power, like you see here on the graph here, this would be called single phase power. Also in North America here, because of the neutral, this is sometimes referred to as split phase. Now this gets a lot different in higher power things like this large generator that you see here on screen, and in aircraft such as the Phantom. If you've ever heard the term three-phase power, if we take that same rotor and we put 3 sets of stator coils on it, but we have to do this geometrically. So starting at 0 degrees, we put, and this is not the scale, pardon my crude drawings, one at 120 degrees and another one at 240 degrees, and then connect them together in a unique way here you'll see shortly. You're going to create 3-phase power because you have 3 sets of power generating coils. So this, you could consider this phase A, phase B, and phase C. This is the principle on which power plants, large generators, aircraft generators all run on. They use 3-phase power because it is far more efficient. And as you can see from the diagram I have on screen of, if you looked at 3-phase power, at no point does the individual phases will cross 0 volts, but if something is running and connected to 3-phase power, at no point does it ever see 0 volts. So it's very efficient to run larger loads, such as a very large motor, a compressor, pumps. A lot of large things will run off of 3-phase power because it's way more efficient to run them that way than it is off of single-phase power. So a lot of 3-phase power does feature a neutral, just like it does here in the Phantom. And what we'll end up with is those 3 generator coils are connected on one end of them. So you'll have L1, L2, and L3. And the center would be the neutral, and this will be important here in a minute when we go back to the airplane. But this would be considered 3-phase Y power because of the shape of the diagram looks like a Y. Now, in the Phantom's case, all right, so if you use a meter and you measured from your phase to the neutral point, you're going to get 120 volts. And a lot of things in the aircraft will run on 120 volts. Now, if I measured from phase to phase, because instead of having 240 volts like in my generator at home, and because of the geometry involved with phase angles, and I'm not gonna confuse things too much, but if I measured from one phase to another phase, I'm gonna get 208 volts, and that's exactly what I measure off of our power cards and in the Phantom. And this is commonly referred to as 120-208Y 3-phase because of this, and a lot of electricians will immediately understand that. But this is how it's arranged in the F4, and a lot of commercial power is very much like this, at least when it gets to the distribution level at buildings and such. Now, almost no generator uses a permanent magnet to create the magnetic field needed for the coils. So in place of having a permanent magnet, the rotor itself will be its own coil, also known as a field coil. And the advantage of having a coil here at the rotor is you can, if you put voltage into that coil, you create a magnetic field. You created an electromagnet. And if you adjust the voltage in the rotor, you control the voltage on your stator coils, and that is the basis of a voltage regulator. And The voltage regulator reads what's happening on your phases and will adjust the voltage of the rotor up or down as needed in order to keep the voltage consistent at the power at your stator coils. All right, so I hope that generator talk cleared up the differences between the single phase and three phase power, because these and a lot of aircraft these days take three phase power. So let's take a closer look at what it takes to actually power this. All right, we are going to start with ground power, and here's the best example is our NC8, a mobile electric power plant, according to Navy terminology. But we have the diesel engine. In this case is a Detroit diesel, 4-cylinder. And so that would be the prime mover of this generator. And farther back, you can just see that big cylinder behind it. That's the actual generator, also known as an alternator in this instance. Whenever the whole unit is referred to as a generator, but when you break down its basic parts, you have a prime mover and you have the alternator. All right, so coming off of that is 120 volt, three phase electrical power at 400 hertz. And that comes out of this plug. So with the three phases, we have A, B, and C, and the fourth phase here, the neutral, which ties them all together. Now, you may be asking yourself, why do we have extra holes? Well, these pins are important because that is what is called the E pin, and that is actually pins E and F on this plug. So E pin power is pretty important. Let's go check out the socket on the aircraft. All right, so here's our power socket, and this is still common on airliners to this day, is this very socket. You have the same corresponding pins, but you notice that the little E and F pins are a lot shorter. There's a reason for that. All right, so up inside the aircraft is a small power supply, and if you guys have been watching this channel for any length of time, you probably have seen us fighting with that before. It's in the panel just forward of the electrical socket that we just saw. So a little bit of electrical power is tapped off of the plug, goes to that power supply, and makes 28 volts. That 28 volts goes down to pin E on the plug. Inside the actual plug is a loop that connects E to F, and that goes back up into the jet and then ends up at, where's my panel? So that 28 volts ends up here at the generator control panel. And in the older Phantoms, it looked like this. In the E model and newer, once they got past a specific tail number, this changed. So the generator switches themselves moved up or moved aft to the cabin pressure panel. The generator status lights here moved up near the canopy rail, so it's more, the pilot would see it a lot better. But the master caution reset stayed put up on the forward end of the right-hand console. So that 28 volts comes up to the generator switches, and when you put them in the down position for external power, that turns on the all the electrical systems in the aircraft, and then it will accept ground power. You have to manually switch it on. Now, the reason why those little pins were shorter than the other ones, so if this plug ever came loose or started to fall out, those two pins would disconnect first, and whenever that happens, the big contactor inside the aircraft would lose its power and would open, and that's designed to break the circuit rather than having the plug possibly have a little bit of an electrical arc as it comes off of the airplane if it falls off. So those two little pins are pretty important. Now, when I mentioned earlier that the aircraft makes that 28 volts and sends it through the plug, that's the older way of doing it. As I understand it, modern aircraft now, the electrical cart itself, the electric source, makes that power, and the loop is on the aircraft side now. So that power that the cart makes goes up to the aircraft, it loops back down, and that 28 volts has to come back to the power cart in order for it to even send power up to the aircraft. So they kind of changed the direction on that a little bit. So that's ground power in a nutshell. Now, a lot of aircraft cannot have both the engine generators and a ground power source connected together. So in our case here, in order to go onto the engine generators, you have to first pass a switch through the off position. And in doing so, it breaks that circuit for ground power, and then it unpowers the aircraft briefly until you put the engine generators on. Now, on the engine side, especially for us, the generators are located at the nose of the engine itself, up inside the ducts. That is normal for an Air Force Phantom. I've had some Navy and Marine ground crew have mentioned the generator is down on the accessory gearbox on the engine itself on their Phantoms versus up inside the duct on a Air Force Phantom. The starter was also a lot different. I think that's the big key difference as to why that is. So if I'm not mistaken, so where the starter is for us on an Air Force Phantom, that's where the generator, I think, is on a Navy and Marine Corps Phantoms. For those of you watching and you know if that's where the generator went, please comment below. I love learning this kind of stuff. But the starter on a Navy and Marine Corps Phantom wasn't there. It was actually further back on the engine. But that is the accessory gearbox that that's attached to, and that's where the generator would have went on Navy and Marine Corps. But since an Air Force bird has a starter there, they moved the starter up to the nose of the jet, or of the jet engine itself. All right, so assuming that we have both engines running, that is the case where the generators can actually work together. Now, if you remember earlier, generators, especially AC power, has to maintain a constant speed in order to function properly. That's what keeps the frequency locked. And since the jet engine goes from idle speed to full speed, you can't direct drive a generator that way. So how does the generator maintain a constant speed? Well, there's such a device called a constant speed drive. And in the Phantom's case, I believe that's a fluid coupling that has a set speed at which it works. And from idle speed to 100% speed, it'll keep the generators themselves spinning at 8,000 RPM. So as long as the engine is between idle and full speed, that constant speed drive has enough rotational speed in order to maintain the generators at a specific speed. And there's a warning in the manuals that says if an engine shuts down in flight or some circumstance like that, once the engine RPM hits about 53%, give or take, the generator does not have, that constant speed drive does not have enough speed in order to maintain that 8,000 RPM, and that generator will drop offline because it just can't maintain its speed at that point. Now, in that AC power box, there's some controls in there. Because they are on constant speed drives, you can adjust the speed of them a little bit. This is not pilot controlled. This is based on the system itself. So whenever you put the switches up to left gen and right gen, what will happen is the speeds of the generators will change a little bit until they're perfectly synchronized, and then a device in that AC power box will close and puts the two generators outputs together so that they both share the electrical load of the entire aircraft. Now, even if a generator does fail, one generator can support the entire aircraft, and they are sized for that. But normal operations, the two are synchronized and closed in together. That's called the bus tie. So that's as good a point as any to also bring up buses. And I'm not talking about transportation, I'm talking about electrical. So the generators will feed various circuits within the aircraft, and then that is basically subdivided into different circuits. You have the right AC bus, you have the left AC bus, you have an emergency AC bus, and you also have an armament AC bus. So you have that main power is subdivided into different branches, and each branch is just referred to as a bus. Same thing when it comes to DC power. You have the battery bus, and then if I spin around, you have the right DC bus and the left DC bus, and then an emergency source as well, and then an armament DC bus as well. And the DC in this aircraft is primarily 28 volt direct current voltage. Now, you can't, the battery can do an awful lot, and the battery is back here. Now, your normal source of DC power is actually powered by the generators through these devices, and some of you guys have seen these before us dealing with these. This is a transformer rectifier, and that takes AC power in through that jack right there, through that cannon plug. It feeds that 120 volt three-phase AC power into this, and what comes out is a lot of DC power at 28 volt DC. This powers the bulk of the DC buses in the aircraft. And again, these are coupled together. There's a bus tie fuse actually just forward of the instrument panel and out on the canopy wall there on the inside. It's a real joy to get to, let me tell you. But that's what these do, and you can lose one of these, and again, they're sized to the point that they can still power the aircraft. And a lot of modern aircraft still use stuff like this to this day. Definitely modernized, but same ideas. 28 volts is very common in aviation electrical, as is the three-phase electrical power. The 120, 208 volt three-phase. So that's the electrical system, and this thing uses a lot of it, as you can see. As the aircraft got more and more modern, electrical power became more and more important, especially as the more electronic systems got involved. So that is aircraft electrical in a nutshell, everyone. I hope you guys enjoyed that. I will be back next weekend for our normal hangar activities. So until then, thank you guys for watching, and I'll catch you in the next one.